Welcome back to ROBT402, Robotic Mechatronic System Design, Lecture 4, Pneumatics, Directional Valves. Today's topics are as follow: directional valves, examples, simulation, and pneumatic circuits. Directional valves. Schematic diagram and functionality. So on this picture on the left side, you will see 3 or 4 ports, T, A, P, and B. So P is connected to the compressor or the high pressure line. T is connected to the tank or atmosphere, and A and B are connected to 2 ports of a cylinder or double acting cylinders. Here at the middle we have a spool. So this is a spool here. Okay, so here the hole is a valve, is a pneumatic valve. So once the spool moves from left to right, we will have a different connections between ports. For example, at the current position, P is not connected to any of the A and B. Once the spool moves to the right, then P will be connected to the B. Or once the spool moves to the left, then P will be connected to the A. So when we pressurize A or the left chamber of the cylinder, then the piston moves forward. And once we pressurize B or the right chamber, then the piston moves to the left. So here again we have a directional valve with 4 ports T, A, P, and B connected to a double acting cylinder. At this specific position, P is connected to A. So A is pressurized, is connected to the compressor, and B is connected to the atmosphere. So once the piston moves to the right or forward, then the air here trapped inside this chamber will be exhausted through this way. And once the spool moves to the right, P will be connected to the B, so B will be pressurized and air could exhaust and escape from this way from A to T. So you see that by moving the spool in the directional valve, we could change pressure of the chambers inside a cylinder. So that cylinder could be a double acting or a single acting cylinder. Again, in this picture, we have a pneumatic valve. However, on this one, we have only 2 ports, A and P. So you see on this specific position of the spool, P is connected to A. Once the bottom is released, then P is blocked and A is not pressurized. This one, this small vent here, is just basically a escape way for the air trap inside this small chamber on the right side. So it's not connected to the main pressure line and is completely isolated from the main pressure line. Okay, now let's try to understand the symbol of the valve. It's very critical, specifically for pneumatic valve, to understand the symbol. Okay, so each square shows one um, status or position of the valve. So for this specific position of the spool, we have one square. We have only two ports, P and A. On this specific position, P is connected to A. On this position, again, we have two ports, P and A. However, P is not connected to A. Now, if we attached these two squares, then we have a full symbol of the valve. On the left position, P is connected to A. On the right position, P is not connected to A. We have some extra components on the symbol of the valve. For example, on the left side, we have this push bottom. That represents the physical or real physical push bottom on the valve. Plus, this valve is a spring return. So once the bottom is released, the spring will bring back the spool to the initial position. So here we have that spring that shows how the valve will return to the initial position. Now let's discuss a more complicated valve. So here we have 4 ports on this valve. P, pressure, is connected to the compressor. T is tank, connected to atmosphere. And A and B are ports that we connect them to the cylinders. Okay, so here on this specific position, P is connected to B. P is connected to B and A is connected to T. So for this specific position, we have one square. So you see that we have also 4 ports on this square, P, T, A, B. On this position, P is connected to B and A is connected to T. The arrow shows the flow direction of the air. So of course, air flows from the high pressure port to the low pressure port and vice versa. Okay, so here A is the high pressure port and the T or tank or atmosphere is the low pressure port. So the air flows from A to T. Now, when the spool position changes, when we release the push bottom here, then P will be connected to A and B will be connected to T. Perfect. Now let's add extra components or physical components on the valve. We want to see how we could actuate this valve. From the right side, we see that we have a push bottom. So we will add that push bottom to the symbol. Plus we have a spring that will bring back the valve to the initial position or normal position. Usually the normal position is the one on the left side. So this square represents the normal position of the valve. And the one on the right side is the operated position. Valves, symbols, and standard. The standard used for the valve symbols is ISO 1219. The symbols used for the individual elements must display the following characteristics. First, function. So it should show exactly what are the different positions and status of the valve, actuation and return actuation methods. that those push buttons and return springs, number of connections, number of switching positions or those squares, general operating principle, and finally simplified representation of the flow paths. So those must be shown in the valve symbol. A symbol does not represent the following characteristics: size or dimensions of the component, particular manufacturer, methods of construction or costs, operation of the ports, any physical details of the elements, any unions or connections other than junctions. So you see that by looking at the symbol of a valve, we cannot understand how big is the valve. We cannot understand what is the manufacturer of the valve, or what are the physical details of the valve or the elements. Directional valve ports name. So the first one, input port or the power port symbol, is number 1 or P letter. Okay, so number 1 or P letter. So this 1 or P will be connected to the compressor. Output or work line port symbol is number 2 and 4 or A and B letters. Those are the ports that we will connect them to the actuators or those, let's say, double acting cylinders. Exhaust port is number 3 or 5 or R, S letters. So these are the ports that will be connected to the atmosphere. So we either use the numeric way of representation of ports or alphabetic representation of the ports. Valve symbols. So here is a very good review for the valve symbol. Each valve switching position is represented by a square. The number of squares represent the number of switching position. So far on those examples that we had in the previous slides of this video or this lecture, we only had 2 switching positions. However, those number of positions could be either 3 or 4 or 5, which is not that common. 3, 1 is common. Okay, 2 and 3 positions are very common, but not 4 and 5. Lines indicates the flow path. Arrows show the direction of the flow. So see what is the direction of the flow. For example, air flows from port P to port A. Shut-off positions are identified by lines in the right angle. So this, you see this small line perpendicular or on the right angle with the main line. So it means that this line is completely shut off. It's not connected to the next port. The connection, inlet or outlet ports are shown by lines on the outside of the box. So if we extend the line to the outside, it means that those ports are inlet or outlet ports. Any of the P, T, A and B ports should be or could be represented by these outside lines. Valves symbols examples. Okay, so here we have 2 switching positions. Why? Because we have two squares. How many ports we have? Okay, so on one position we have 1, 2, and 3. So what is the symbol then? The first number is number of ports, 3, and the next one is number of switching positions, 2. Okay, so this is a 3-2 valve. This one, we have again 2 ports, 1, 2, but the same number of positions as the previous one. So this one is 2x2 valve. The next one, we have 3 ports, but 2 positions. On this one, we have 4 ports, 1, 2, 3, and 4. So this one is 4x2 valve. This one, we have 2 switching positions, but we have 5 ports, 1, 2, 3, 4, and 5. So I want to remind you about the meaning of these numbers. 1 was the power line attached to the compressor. 2 and 4 are working line. 3 and 5 are tank or atmosphere lines. So you see that on one position, the air will be exhausted through the port 5. However, on the other position, the air will be exhausted through the port 3. Okay, and it's very common. 5x2 valves are very common. This one, we have 3 switching positions. How many number of ports we have? 5. 1, 2, 3, 4, 5. And on this one we have 4 switching positions, and we have 5 ports on the valve. 1 is the middle one. Compressor 3 and 5 are atmosphere ones. 2 and 4 are working line. So usually, as you could see, atmosphere and tank ports are on one side and the working line ports are on the other side. Understanding the symbols of the valve are very critical, because then coming slides, once you start to use fluid sim, you will see that you need to identify the type of ports by the symbol. Okay, so we have some industrial valves and applications here. This one is normally closed one, and you see the symbol here. We have 3 ports and 2 number of positions, 2 number of switching positions. It could be actuated by a push bottom. This is the push bottom here, and this is the spring return valve. So you could see the push bottom, you could see 1 and 2 ports here, but the 3 port is not visible from this side. This one is the normally open one, and you could see the difference between the symbols here on top of each other. Methods of actuation, mechanical ones. This symbol shows a general manual operation. So what does that mean, general manual operation? So it means that the manual operation could be any of kind. This one is more specific. It shows that the mechanical manual operation is a push button. This one is a lever operated, And this one is a dented lever operated. So what is a dented? It means that you need to release it again manually, otherwise it won't be released. On this one, for example, if this is a spring return, then it will be released automatically once we basically move our hand. On this one, we have to release it again. Okay, so here we continue with the mechanical methods of actuation. This one is a foot pedal. So you will activate it by pressing your foot on the pedal. This one is roller operated, very similar to a micro switches you have on MPS 500. So it means that there should be a mechanical contact between a device and the roller to actuate the valve. Idle return roller, this one. So you could actuate it from one direction but not the other way. Okay, so if for example, if a mechanical part approaches the roller from a bottom to the top, then it will be actuated, but the opposite direction, it won't have any effect on the roller because it will break from this pivot point here, and then the valve won't be actuated. Spring return means that we have a spring that will return the valve to the initial position. For example, for the foot pedal, if it is loaded by a spring, once we press our foot on the pedal, it will be actuated. Once we release or remove our foot from the pedal, then it will back to the initial position by the spring. And a spring center specifically are good for those with a 3 number of switching positions. We have 2 springs that keep the status of the valve on the middle position. Mechanical activation. Here we have used a Festofloyd sim. You will see these applications once you start working with the Festofloyd sim in coming slides. This one is a roller, mechanical roller. So you see that once this surface comes in contact with the roller, then the port will be actuated. Once this surface goes away, for example, to this area, then the roller will be released by, or the valve itself will be released by this return spring. We have this symbol that represents the compressor, this symbol that represents the exhaustion to the air, and we have numbers. 1 shows that we should connect this port to the compressor. 3 means that this is an exhaust port, and 2, this is a working line that goes to the actuator. This is non-activated and activated. Once it's not activated, you see that what is the status. 1 is not connected to T, but T is connected to 3. 1 is activated, 1 is connected to 2. Methods of actuation, pneumatic and solenoid. So we have more advanced methods of actuation rather than using a mechanical force. The first one is a direct pneumatic actuation or the piloted pneumatic actuation. So we will discuss the differences and details between them later, but how do they work? We are using a pneumatic force and power to change position of the spool. In direct pneumatic actuation, single solenoid operation. So on this one, we have combination of solenoid and pneumatic actuation. So that solenoid will open or will close the passway of the pneumatic line. And we have a double solenoid operation. Okay, so on the double solenoid operation, we have one solenoid, let's say, on the left and one on the right, and you see that we are actuating or we are moving the spool by solenoid. So we are only using electrical power. Methods of actuation: pneumatic, pilot operated, manually overrided. Okay, so this one is a complex example that you could better understand how the system works. So on this one, we have two manually overrided push buttons. Okay, so if you use these push buttons, you will override the control signal of these pneumatic lines 1, 4 and 1, 2. It is a pilot operated. Why? Because we have a separate passway. This is a separate passway 1, 4 and 1, 2 to actuate or move the spool. Those pneumatic ones which are not pilot, it means that we are getting a internal passway from port, let's say 1, that goes to the back of the spool and will actuate the spool. However, on these ones we have a separate port. Okay, 1, 4 and 1, 2. And these are those push buttons. These are those push buttons that we could manually override the signal that comes from 1, 4 and 1, 2 ports. Main ports are 1, 3, 4, 2 and 4. How many number of switching positions we have? 2. So 1, 4 and 1, 2 are pilot lines or ports. Okay, we'll continue with the methods of actuation solenoid. On this one, we are using a solenoid. So this is a spring offset model, spring solenoid shifts spring loaded spool. So we are using a solenoid to shift the spool back and forth. So we are using electrical power solely to move the spool. However, the spool is also equipped with this return spring. That return spring will push the spool back to the initial position once the solenoid is released. Example 1. We want to design a pneumatic circuit, and on this one we want to have, on this circuit, pneumatic circuit, we want to have a direct control of single acting cylinder. So let me remind you what is a single acting cylinder. We have only one port, one main port, and there is one internal spring that will bring back the cylinder to the initial position. With the positive control signal, okay, so what is the positive control signal? Sorry. So positive control signal is pushing the thumb bottom. So we want to press or push the thumb bottom, and then we want this cylinder to move forward. And negative control signal is releasing the thumb bottom. So if we release this thumb bottom here, okay, if we release the thumb bottom, then we want the cylinder to move back to the initial position. And you see, this is a 3-2 normally closed valve. Okay, so this is the example. I'm going to show you the solution here. I expect you now to open the Festofloyd seam, run it, and try to build this simple circuit. So what you need to do, you need to choose a single acting cylinder from the left panel, drag and drop it, and choose a 3-2 valve and drag and drop it. If you double click on the valve, you could change the type of the valve, number of positions, number of the valves. You could change the method of actuation. You could either equip it with the spring return, or you could remove the spring return, basically part, and if you double click here on the exhaust port, then you could choose this specific symbol, or this rectangular or top-down rectangular. This one from the left panel, you could drag and drop it. It is a compressor, and then you could easily connect these ports. Okay, so you could build your circuit, run it, push it here. Okay, click on this thumb bottom and see how the actuator will react. Here we have a schematic diagram of the pneumatic valve and the cylinder. So on this position, compressor is not connected to this chamber, so nothing will happen. Once we push this thumb bottom, then the compressor will be connected to the left chamber. This one, the pressure will increase and will push the cylinder forward. So you see what is the positive control signal? Pressing the push button. What is the negative one? Releasing the push button. By releasing that, the cylinder will move backward. I will prepare a separate video, and I will solve 1 or 2 example or homeworks in the Festofloyd seam, so you could see how you could work with the Festofloyd seam. But I promise you, is a very intuitive software. If you start opening up and create a new file and project, you could easily drag and drop these components and attach them together and run the simulation. So try before watching that video about the Festofloyd seam. Example 2, we want to have a direct control of single acting cylinder. On this one, we want to have a positive control signal, which is releasing the thumb bottom, and negative control signal is pushing the thumb bottom. So it's exactly opposite of the previous example. On this one, we are using a single acting actuator and 3-2 normally open valve. So only the initial position of the pneumatic valve is different from the previous example. This is a solution. Again, try to simulate it in a Festofloyd seam. You could change the initial position if you double click on the pneumatic valve, and then you could change the initial position from one to the other one, and basically modify the previous example and make this example possible. Example 3, direct control of double acting cylinder. So we have a double acting cylinder. You see we have two ports. What is the positive control signal? Activating two thumb bottom control valves. So we want to use, on this specific pneumatic circuit, we want to use two 3x2 valves. One is normally closed and the other one is normally open. A negative control signal is releasing the control valves. So once we press these push bottoms, once we press these push bottoms, we want this cylinder to move forward. Once we release it, then the cylinder should move backward. Solution example 3. So on this one, see we are using these two valves, and let's see what is exactly the status of the system now. One is connected to two, so this chamber has a high pressure. However, this chamber is connected to the atmosphere. Okay, so now the cylinder has moved forward. Once we push these push bottoms, then the status of the pressure in those chambers will change. One will be connected to two, so this chamber will be in a high pressure, and two will be connected to three, and this chamber will be in low pressure or atmosphere pressure. So we expect to see the cylinder move backward or from left to right. Again, do it in Festo-Floyd Sim. Start to get your hand dirty with the software. It's very intuitive and easy to understand software. Double click on the valve and double click on the cylinder to change properties of the cylinder. And you could add a spring, remove a spring, change the number of ports on each of them. You could change the type of the rod from a one or single-ended rod to the true rod or double-ended rod, and so on and so forth. Basically, you could, if you double click on each of these components, compressor, valve, and actuator or the cylinder, you could change their characteristics. Okay, so let's watch this video that these students are using components of the example and making a real pneumatic circuit. Okay, so we have a 3x2 normally closed and normally open valve. We have a single acting actuator and a double acting actuator. That the small vent is for the single acting actuator to basically release the trap air inside the cylinder. Okay, so now he used one of these valves to control a single acting cylinder. However, to control a double acting cylinder, we need to use two of these 3x2 valves. So you see it's push, release, and the cylinder will back to the initial position. This one is a double acting cylinder. You could identify that by seeing two ports on the cylinder. Now he's basically just rewiring the circuit. Okay, so push and positive control signal and negative control signal are basically uh, um, are provided by these 3x2 valves. Here he is showing us a valve which does not have the open shell, so you could see what are the internal components here, the cylinder and the cushion here. This is a cushion here and the rod and 2 ports. Okay, so you see the cushion here and the main piston and 2 ports. Example 4, we have a direct control of double acting cylinder, or we want to have direct control of double acting cylinder. Positive control signal is pushing the thumb bottom, and the negative control signal releasing the thumb bottom. So here we need to use a 4x2 valve to make this circuit possible. So if we want to use only one valve with a double acting cylinder, that should be at least 4x2. That cannot be 3x2. Okay, so on this one, you see on this position, 1 is connected to 2, so 2 is pressurized, and then 4 is connected to atmosphere. What is this valve? This one is mechanical operated with the push bottom and spring loaded. Here we have a cushioning here, which is variable, and you could change the degree of cushioning. How you could change your cylinder to this specific symbol in the Festool sim, just double click on that, choose a cushioning option, and then you could have a cushioning on one side or two side, or variable or fixed. What is this symbol? This one is a muffler. If you double click on the port or the exhaust port, then you could choose a muffler. Muffler is used to reduce the exhaustion sound. Okay, so those pss, pss, pss sound that is audible from the valves and pistons could be reduced by these mufflers. Homework. Okay, so the name of this section is homework. However, we will provide the solutions because you are learning as we are going forward. However, why did I choose this name homework? Because I expect students to make all circuits, although the solution is provided, I expect them to make those circuits in Festool sim and submit them on Moodle. So my recommendation to you is, if you want to understand deeply this section, to pause on the problem, try to solve it on a Festool sim simulated, tested, and then if you could come up with the solution, excellent. You could then look at the solution and see if an alternative solution is provided, or if you have managed to come with a feasible and working solution, then you could look at the solution and see how you could accomplish that circuit and learn from that homework. So I want to remind you that there is no unique solution for pneumatic circuits. There could be couple of different circuits that work the same. So there could be some alternative solutions provided here than the one you managed to come with. The first homework, indirect control of double acting cylinder. Okay, so we have an indirect control name here. I will explain it on the solution. What do we mean by the indirect double acting cylinder? You know, positive control signal is manual actuation. So once you, let's say, press the push button, then you expect the cylinder to move forward. Negative control signal, releasing the manual control valve. What type of valve we want to use, or main valve, is 4x2. Okay, so since you don't know the meaning of the indirect control, then you may want to move to the next slide and learn from this homework. But again, I expect you to make the circuits of all homeworks and submit them on Moodle. So here we have a main valve. We have a main valve here. It's 4x2. We have a double acting cylinder, and you easily know that once the one is connected to 2, then we have the cylinder retreat to the back, and once 1 is connected to 4, it moves forward. However, this is not a direct control, so it means that we don't have that mechanical push button here. This is an indirect control. It means that this valve is a pneumatic actuated, so we have another valve that controls the main valve. We call this valve control valve. So this control valve, once we press this push button, 1 will be connected to 2, and this main valve will be actuated. And once we release that push button, that the spring will return back this valve to the initial position. So 2 will be connected to 3. So the pneumatic power will be released from the back of the, or the top of this spool, and the spool will retreat back to the initial position by this spring here. So that's why we are calling this circuit indirect control, because we are not controlling or manipulating the main valve directly, but we have another control valve here that actuates the main valve. Now you know the concept of indirect control. Homework 2, indirect control of double acting cylinder. So exactly same as the previous one so far. Positive control signal, manual actuation, and negative control signal, manual actuation. So the only difference between this homework and the previous one is that the previous one, negative control signal was releasing the push button. And the main valve is same as the previous one, is 4x2. So if you manage to build your circuit on the previous one, you could modify it and make this circuit possible. Here we have the solution. Main valve, indirect control, double acting cylinder, positive control signal, pushing this thumb bottom, and negative control signal pushing this thumb bottom. So it's not like the previous one that we had the spring, and by releasing the push button or thumb bottom, the control valve could back to the initial position. We need to deactivate the valve. manually. Homework 3. Indirect control of double acting cylinder. Same as the previous one. Positive control signal will be a manual actuation. Same as homework 1. Negative control signal, releasing the manual control valve, same as homework 1. However, on this one or on this pneumatic circuit, we want to use a 5x2 main valve. So again, I remind you, please try to modify the previous circuits, build the pneumatic circuit in Festo-Floyd sim, test it by yourself, and then move on to the solution. So what industrial parts could be used in this homework 3 double acting cylinder, 5x2 valve, and let's see if we need to use this 3-2 valve for the indirect control. Okay, so here we have this double acting cylinder, 5x2 valve. We have 3x2 valve, which is a control valve. This is the main valve, is connected to the actuation. Once we press this, let's say push button here or the lever, then the main valve will be actuated. Once we release it, it will back to the initial position. The pressure here on this line will drop, and then the spring could manage on this main valve, could manage to bring back this valve to the initial position. This is a monostable 5x2 valve. What do we mean by monostable? It means that it could be positioned on one of these, let's say, squares. Okay, so it could only be in one position once a time, and once we release it, it will back to the initial position. That's why we call it monostable. We have other types as we go forward. We see. I'm gonna stop this video at this point. I think we had enough for this video. And on the next video, we'll continue with the homework, and I will have another video for you that I will solve one homework or example in Festo-Floyd sim, so you could see how to work with Festo-Floyd sim. Preferably, I will solve one of the more advanced homeworks as we go forward, so you could have a more comprehensive video on Festo-Floyd sim and see how you could use and work and change different components. But I'm gonna stop this video at this point, and then we'll continue on the next video.